In this video, we will have a detailed look at how a decision tree will partition the feature space in different subregions and how we can make predictions inside each subregion. So remember that the goal of a decision tree is to split the feature space in a number of smaller subspaces. And what we want is that the variability inside each subspace is relatively small, so it is easy to make predictions in a subspace, or at least easier than it is in the whole predictor space. So a decision tree is a tool that provides a step-by-step plan to partition the feature space using binary splits. So it's step by step. It means that we are not going to directly split the feature space into several different subspaces, but we will first divide it in two parts, then take one of these parts, again divide it in two parts, and so on. So it means we have a binary split. So we start with the feature space R, which we call the root node. And in the first step, we will say, well, let's split that root node in two parts, R00, R01. And of course, R, the whole feature space, is equal to R00 together with R01. So we take the whole feature space, we split it in two parts, where we call R00 the left child and R01 the right child. Then in the second step, we take either R00 or R01 and we split that again in two parts. And then we can take another node, split it again in two parts. And if we continue like that, we create more and more subregions of our feature space. In this figure, you see what happens if we do consecutive binary splits. We start with the root node, which is the R0. And we divide the R0 in two parts, where we call the left child R00, where the first 0 means that it's a child from the root node R0. Same for here, we have R01. The first 0 indicates who was the mother of this node. Then we have a second 0 here and a 1 here. That indicates whether you have the left child or the right child. The root node is of generation 0. We call these two nodes generation 1. And of course, we start with R00, and this R00, R01 together gives you back the whole feature space. If we take, for example, this node here, the left child R00, then we can again split that node in two parts, R000, R001. And if you look at the notation, you have R00 and here R00, which indicates that the mother node is this one, and then you have the 0 here, the 1 here, to indicate you have the left or the right child. And we can do the same for this node. We can split it into new parts. And then we have that R00, this one, is just the union of these two, and the same for R01. And these nodes here are generation 2 nodes. We can split also this one into new nodes. In this tree, we have that this node, this one, this one, this one, and this one are nodes without any children. So these nodes are not split into new nodes. And that's why we call these nodes leaves. So we have here a decision tree with 5 different leaves. And if you look at the leaves, then the union of all the leaves gives you back the root node. So in the first split, we have that R0 is the union of these two new nodes. And then we use the notation zeta0 to indicate the split. So zeta0 means we split the root node R0 into new nodes. And because we split the node in two parts, it's called a binary split. We can then have the split zeta00, which is the binary split for R0. 0, 0. And the same for zeta 0, 1. Assume we have a node RT in our decision tree and say the node is of generation k. Means that you have k plus 1 different 0 or 1s. For example, if k is 4, it's generation 4. So then we start always with a 0, meaning that we start from the root node R0, and then we have 4 different splits, and we have the first 0 here indicates you have the left child, then you have a 1, meaning you go to the right child, and so on. Then zeta t is the binary split for the node RT. We divide RT into new nodes. And these two nodes together gives us back RT. So the union should be RT, and it should be non-overlapping, meaning that any element in RT is or in the left child or in the right child. So now we have a way to split nodes. We start from the root node and we split the root node in two parts. We take one of the children, we split it again in two parts, and so on. The question is then, when do we stop? Because we can keep splitting, but of course we have to stop somewhere. We need a stopping rule. And for example, a stopping rule is that you only split a node if the decrease in the variability in each of the subnodes is significant. So you want to split a node into two different nodes because the variability is small and you can do better predictions. But of course, if you only improve a slight tiny bit, maybe then it's not worth to do the split. So that could be a criterion to decide if you want to split a node, yes or no. If you have a decision tree, we put all the nodes in the set T. I already said that there are nodes that have no children, that are not split further, and these are what we call the leaves of the decision tree. And the set of all the leaves is noted by this T. So if we have a node in our decision tree, then if it is in this set T, it's also a leaf. And then of course you have this, that all the leaves are also nodes in the decision tree, but not the other way around. If you do a finite number of splits, then we end up with a finite number of leaves. And assume that we have in total m leaves, which I denote by R1, R2, R3, all the way to Rm. Then we have that the initial predictor space R is the union of R1, R2, R3, and so on. So we have a feature vector x, then we know that the feature vector x is a member of one of the leaves of our decision tree. So we have to look which leaf is the one where my x belongs to, and then I can predict inside that leaf. If we split a node into two parts, there are actually a lot of ways that we can do that. For example, assume that we have x1, x2, and assume that the feature space is 0, 1, 0, 1, this square. And assume that a binary split is splitting this space in two parts. Then, for example, we have the following division. We can say we split it in this way. We have part 1, we have part 2. But we can also have a different way of splitting the same space into two parts. Also in this case, we have here 1 and all the rest is 2 is also a binary split of the feature space in two parts. If we look for the best split, means the split that gives us the biggest reduction in variability in each space, subspace, we have to consider a lot of different splits. We have to search over all the splits and see which one is the best. But if we allow for all these exotic ways of splitting the feature space, it's a very hard and difficult problem that takes a lot of time to compute. And therefore, on the next slide, we will make the problem more tractable by only considering a subset of possible splits. So we will not allow this split or this split. If we split a node in two parts, we only consider so-called standardized binary splits. So assume that we have a quantitative variable. So x1, x2, x3, all the feature variables are quantitative just for simplicity. Then we say, if we do a standardized binary split, then we look at RT and we split that in two parts, RT0, RT1. When does a certain feature vector belong to the RT0? It's only when we have one variable XL, so we have P predictor variables in total, but we only consider one dimension, and we say as long as XL is smaller than C, we are in RT0, and otherwise we are in RT1. So it means that we have P feature variables, but in order to split RT, we only look at one variable. For example, assume we have x1, x2, again we have 0, 1, 0, 1. This is our RT space. And we have to split this in two parts. One split that I mentioned on the previous slide is this one. But if we want to do this split, we have to consider both x1 and x2. So we will not allow this type of splits. Instead, we will say, well, you have to pick one dimension. For example, we split along the x1 dimension. It means that there is a C here, and everything that is on this side is RT1, RT0, the left child. Everything that is here, larger than C, is the right child, RT1. In case our feature variables are categorical, we cannot say, well, it should be smaller or larger than a certain value, because my x values are now categories, class 1, 2, 3, and so on. In that case, I will again focus on one dimension. I will just take one feature variable, XL, and say, well, you belong to the left child if XL takes classes in C, where C is a subset of all possible categories. Assume XL indicates whether you are a good, a bad, or a medium driver. Then C could be good and bad. If you are a good or a bad driver, you belong to the left child. If you are a medium driver, you belong to the right child. But what is the similarity between this one and this one? Although it's quantitative versus categorical variables, we only look in one dimension. We look at all the feature variables, we pick one, and we say we split along this dimension. And that's what we call a standardized binary split. Assume that we build a decision tree with leaves R1, R2, all the way to Rm. And we have a feature vector x. Then we know that x belongs to one of the leaves, because the feature space R is equal to the union of all the leaves. And since x is in the feature space, x belongs to one certain leaf, Rj, say. How do we then predict the response y hat, which corresponds with this feature vector x? We have the lambda I, which is the prediction for leaf I. So it means that if I'm in leaf 1, my prediction is lambda 1. If I'm in leaf 2, R2, it's lambda 2. Then I take a sum here. I take the lambda I and I take this indicator, which means that this is equal to 1 if what we have here is true and 0 else. So if x is in leaf Ri, we get lambda I as our estimate. Because the leaves R1, R2 are non-overlapping, we have here a sum I going from 1 to m, but there is only one term that is non-zero. All the other terms are 0. For example, if x is in R1, then x cannot be in R2, it cannot be in R3, and so on. So then only we have lambda 1 times 1, and all other lambdas are multiplied with 0.